Thank you, Ben. Thank you for the very kind introduction there. It's definitely a pleasure to be here at the JK every couple of years, every couple of years. And it's definitely, and this topic is a particular topic that I'm very fond of speaking to this audience, because actually it's a little bit like preaching to the converted, but really talking to people who, a lot of the people really understand and recognize that. So it is, I'll be talking to you about this Mechanistic Comminution Modeling success story that has not yet ended. A little bit looking back, and really the outline of my presentation is going to be, after a brief introduction, exactly like Ben anticipated, the breakage modeling. We think it's a very important part of this approach. So we look into breakage modeling, and then after that look at how we should and can tackle the different type of comminution machines using this mechanistic approach, looking at mills and crushers, and then we go to some conclusions. Well, just you can find a number of definitions of mechanistic modeling. I think this one is simple enough, and I think captures quite a lot that we want to convey in our approach, which is, could be the definition, description of a complex system from examining the workings of its individual parts and the manner in which they are coupled. I think this is really good, because exactly what we want to do when we have a complex system is to be able to break them apart, analyze into smaller and more understandable parts, and then we can actually put them together as we see fit, exactly as it is in practice in comminution and our different processes. And well, what do we want when we actually apply this approach to comminution? We want to be able to do exactly this decoupling, which is decouple the material, which is the ore, which has all its complexities, certainly as far as breakage is concerned, but also the complexities of the size reduction machine. So we want to understand and decouple these two in a much better way that was done in the past using the traditional population balance type of models and phenomenological models. And I think one bonus that we believe we get from this type of approach is that when we properly decouple, we can actually understand and characterize the material and apply it across the whole spectrum of unit operations. That's the vision, the desire, something that we are pushing forward. And of course, what we always have an opportunity when we actually look deeper in a process like that is to be able to perhaps look outside the box of perhaps the operation of those machines that already exist, be able to better customize the machine to the type of feed or ore that it's going to receive, but certainly be able to look at other machine configurations using this capability. So there's plenty of motivation, I believe, to pursue this path. Well, but who did the work that let us actually come to this point today? Certainly, I think the 20th century was really a fantastic century for comminution. I think a lot of bright people paved the way. For instance, understanding and quantification of breakage. If you read the papers from the 1950s and 60s from a lot of these guys, they were right at the same moment that fracture mechanics were really blossoming, and they were doing top work, and they were actually comminuters, and quite amazingly. And then if you look in basically the two schools that I definitely look at, in Germany and Japan, fantastic papers. Of course, but then we take a lot of advantage of the application understanding using the traditional population balance models, because in the end we want to be able to use that type of framework to guide us through the more complex processes, but of course now using much more detailed descriptions of what's going on in those kernels. Of course, a lot of important people here. Well, nice Bill today with us, and of course Alvin Lynch here in Australia. And finally, at last but not least, one of the important pieces of the puzzle that allow us to actually even look a little bit deeper into comminution machines is, of course, the discrete element method that was not developed by these guys, but definitely first applied to comminution and back in the University of Utah in the early 90s. So those were the people that actually, in my opinion, make the greatest contributions. And then, of course, I borrow from the late Peter King the title to my presentation today as an honor, because actually he 25 years ago, he actually pretty much did this, reviewed what was already done in the past in comminution, that actually led us back then in 1993 look in the future as a potential approach to comminution modeling using especially more mechanistic models. So that was a very nice review, pretty much looking at what was the understanding back then and what were the tools that were already available, but certainly the challenges here was very clear back then. Well, 21st century already in quite a few years. Quite a few people now have been working very actively in this area of mechanistic modeling in comminution. We can just name a few of those people there, quite a few in the audience here, a couple. But really, we in Brazil, pretty much what we did is take the inheritance of what was done in Utah, consider that Professor Piliquim passed away in the early 2000s. And so we thought that there was an opportunity to start a group exactly along that vision. And so we started this school in Brazil, I'd say, looking exactly into that. Of course, as I mentioned, looking at advanced comminution models pretty much requires us understanding the detail of what's going on, the energy transfer. And DEM has been a fantastic tool. I think in this room probably you have seen dozens of presentations just dealing with that. No need to review it, but I think I was definitely very proud to be early in the 1990s in the University of Utah when Rajamani and Mishra applied to ball milling for the first time. And of course, this technology has been evolving very nicely in the last several years, with particular interest here to GPU technology as it pushed it even forward. But of course, there remains really challenges in this area, and we have to be still bright on how we use that technology before computers really go and solve our problems by being more and more powerful. We are not quite yet. That's how we need to properly tackle the challenges that we have ahead. So, looking at the first piece of the puzzle, in my opinion, on how to build a proper mechanistic model, it is really to understand the building blocks in comminution, which is the single event that a particle is stressed under some conditions. And so this is a key piece of the puzzle in comminution modeling in advanced models. And my idea is that really the breakage model, to be able to fit, to suit the needs for this type of approach, it should be able to, for instance, cover all aspects of particle response. It has to go beyond the simple drop weight test. It has to go beyond just the energy size reduction relationship. It should be able to discriminate between the different breakage mechanisms in a much deeper way than we do typically. It should be amenable for calibration using relatively simple tests. And remember that in comminution, we're no stranger to testing. The industry spends a huge amount of money, sometimes doing 20 different tests to cover different potentially usable machines. And I think we can definitely do a much better job by doing maybe very detailed, but tests that can actually be portable from one machine to another. And that's the vision, to describe the mechanisms. And of course, be valid over a range of sizes, because a wide range of sizes, because in the end of the day, we're going to be covering anything that is coming from the mine, from boulders, down to sometimes very fine grinding. So we have to be able to cover as much as possible all the spectrum, and not just assume that if you understand one size, you'll be able to just take for granted what happens in the final sizes of the very early on. So you see some evidence here, and that's the idea, that those are the requirements, in my opinion, for those breakage models. So in order to understand what we need to be able to characterize when you actually model breakage to this level of detail, I think it's educational to see that in the end of the day, the model has to be able to answer these questions. What happens if a particle is stressed under a given condition? What is the outcome of any event like that? Each single event. So, for instance, what happens? What is the chance that a particle will break at a given event, given stressing condition, given size, and so on? Well, we have done a lot of work back then, back in my time in Utah, to use, for instance, a device like this, ultra-fast load cell or impact load cell. You guys call it short impact load cell. It's just because impact is an important method of stressing particles in industry. We can actually test particles one by one. It is a very tedious test, of course, but the outcome is something that is very enlightening, because I think you can, for instance, look at this very narrow size range, and you can see here each of those is a different particle containing the same size and the same composition. And you can see here that that's the amount of energy that's required to break each of those particles. You see, even for the same material, it's an order or 2 orders of magnitude between the toughest and the weakest. So variability is part of our business. We have to understand variability. And just describing as averages, we get away a lot of the time. We know that power models are good, power, energy size, reduction relationships cover a lot. But if you want to know the details, we have to account for this variability. And the variability is not an issue. We're not talking about experimental error here. It's actually natural material variability because of variability in cracks and everything. So the nice idea from this is that you can discriminate between materials. There is variability, but there's still clearly a fingerprint that you can measure. And just looking at one parameter here, like the median value, just to be able to compare, if you keep track of these numbers here over the size spectrum, for instance, looking at the graph here, that's now the median value as a function of particle size. You see here a huge range of sizes from 100 millimeter particles down to about 200 micron particles. You see those natural trends that you expect from brittle materials. As they get finer, they are tougher. That's quite obvious. All the comminution laws more or less cover that. But what is interesting, I believe, in this is that it's not a single law. It's not a single slope. And further, for some materials, actually it becomes constant here. As we know from school, I don't know, second or third year mineral processing, we talk about Kick's law. Yes, indeed, Kick's law very often is valid because here for coarse particles, sometimes their strength becomes nearly constant. On the other hand, for some materials, that is not quite true. And, well, should we concern ourselves about that? Maybe, but we can measure. The things that if you can measure, later we'll bother about explaining that. And in fact, if we borrow a little bit from fraction mechanics, we can actually even go a little bit further trying to explain what happens here, which explains why this increase is so steep at fine sizes, which we understand that cracks are the ones that are defining fracture, initiation of cracks. Whereas if you look at very coarse sizes, you're dealing with very complex particles, and they actually crack initiation is not an issue. It's actually propagation of cracks within the microstructure that eventually creates this constant strength. Well, besides being able to explain this, the most important thing is to be able to characterize. Because by looking at this, you'll be able to see interesting things that we know from practice, which is some materials are actually very hard to crush, but actually they become not so hard to grind. We know that. Sometimes it's a good, sometimes it's a bad surprise. On the other hand, there are some materials like this, pretty straightforward to crush, very low energy required. On the other hand, as you go to fine grinding, it really gets tough. And we know that's the reason why industry puts a lot of money testing, but we should be able to explain and characterize that independently. So it's just as answering the first question here, which is what is the chance that a particle breaks? If it does not break catastrophically, what happens? Every time you hit a particle it doesn't break, well, we know that it does get weaker. If you hit it over and over and over again, eventually it does break. And we needed to look into that, and that's also back in my PhD, we developed this fracture, this continuum damage mechanics model. It's a very simple model, just a single fitting parameter that allows us to actually predict something or fit something as simple as this. What is the likelihood that you break particles as you increase the number of impacts and the impact energy? So these lines here are the model predictions, the points are experimental data. So this is an important piece of the puzzle that was lacking in all the work back then, because with DEM, the work done here in a number of places, we started to realize that a lot of the energy in mills and even crushers is really well below the required energy to crush particles. But that doesn't mean that it's all wasted energy. It actually still does something. And depending on the level that it is, it does good work, sometimes it does very little work, and that's exactly what we can understand through this. Well, just going forward that if it doesn't break catastrophically, besides getting weaker, it really gets a little bit of rubbing on the surface, which we call attrition or abrasion or even chipping. Yeah, this is really a tough topic. I think most and Malcolm have really put a lot of time, a lot of effort into this, and a lot of people as well. We actually got a little bit satisfied with applying recently a model from Mojtaba Gadiri in Leeds that actually established a relationship between the energy that is dissipated every time a particle impacts considering the shear and the normal energy and the amount of debris that is left. The only reason why we got successful on this because we use iron ore pellets as model materials because they're really nicely round. It doesn't go through the funny rounding process. So it is satisfactory, but still an area that requires a lot more knowledge. But for our purposes, I think it is doing a good job. And the last question does answer it is, if it does break catastrophically, that is, if you put enough energy, how would the size distribution look like? But that's pretty much our bread and butter in comminution. We know drop weight testing, impact testing, we do that. We just did some tweaks in this model to be able to just cover what is actually breaking, never analyze material that is just suffering surface abrasion, not to mix the two mechanisms. But except for that, it's very simple to do T10 procedure that was developed and used a long time ago. So just to illustrate what this really entails to put these things together and the importance of this breakage probability, in my opinion, because if you look at the size spectrum here, it's huge. 1 joule per kilogram, all the way, I don't know, to 1 million joules per kilogram. And you look here right in the middle for this particle size, we have the breakage probability distribution, which looks very steep, but of course you have very wide size range, wide energy range. What actually happens is that if you stress particles at this low energy, you only get surface breakage and some weakening. That's obvious. If you stress at very high energy, that's where you have particle catastrophically breaking that we call body breakage. That's just fine. And this we have been very successful characterizing in T10 and everything. The problem is that in this region here, you exactly have the transition between the two things. And that transition you have to capture, being able to understand what fraction of the particles that happen surface breakage and how much material actually surface breakage. And the funny thing is that when you put the models together, you get this little kink here, that if you're not careful enough in your experiments, you never get that. So it's you have to be able to decouple the mechanisms to put them together, because the machines will do all different compositions of this. And the obvious result, of course, we know in comminution, that's why energy size reduction relationships are so robust. That as you increase the energy, of course you increase the amount of breakage. But really, are you describing this accurately enough? We think we weren't in the past. I think we are in the right path now. And just to give an appreciation of how important we think it is to understand these distributions, it is, for instance, if you look here in blue, the strength distribution of materials, the energy required for breakage in blue, and then we compare to different distributions here, for instance, collision energies. If you apply very high energies to a population of particles, that's not a problem. Everything will break, and the T10 procedure that we know well will describe it, no big deal. On the other hand, if you apply very, very little energy, nothing will happen, just a little bit of debris, and there's no mathematical complexity in this. It's just a simple equation you calculate. Well, what happens in practice starts to approach this, which is like a hammer nail or VSI. You're right in the middle here, but really, really in practice in Mills and Crusher, it's not even that. It's actually two distributions that overlap, because the strength distribution is wide and the stressing energy distribution is wide. This is a typical problem that requires a convolution or a deconvolution to be able to take care of this. So this is something that was known way back. But exactly back in the 70s, people didn't have DEM to be able to get this red distribution. We actually only had the blue one, which is the fantastic work done by the Germans and so on. So for instance, one interesting thing that we can get from understanding breakage is that realization that what is the optimal stressing energy that you should apply to be able to do the same job with the least amount of energy. So, for instance, here, the x-axis is how much energy you're applying to each impact divided by the mean energy that requires to break all particles of that size. Let's use the simulation feet minus 8 millimeters and the product of a given size. You see here for a number of materials, you get quite variable curves, which obviously say that if you overkill the particles, put way too much energy, you waste energy, obviously, and this goes to the roof. But if you're getting too conservative here and applying too little, it goes actually, again, being inefficient. We know that there is an average number here that is the optimum. And it's the interesting thing is that it's not, sometimes it's quite wide depending on the material, so it's quite forgiving. Some materials really have allow us to stress under variable conditions and still give reasonable energy consumptions, whereas some other materials, this is quite a steep one. So very narrow range that you can get optimal. So this is something that we can get out of putting together into a very simple experiment, virtual experiment, which is impacting particles successively at a given energy. So now that we believe we have something that makes sense as far as breakage modeling, how can we move into the direction of using this to predict something of use in practice in a comminution process? Now we go to an important point, which is how can we couple this information to DEM? There are two options. First is that can we actually do this separately from DEM? Because anyone who works with DEM knows that obviously the number of particles that you have in a simulation is going to impact quite a lot the computational effort. So the first option here is that can we get away with the problem of just simulating the grinding media in the mill or a system and just do as a post-processing tool the breakage prediction? And the second part is that no, in some equipment you cannot do that. You have to have the particles breaking, otherwise it won't be realistic. A crusher is a very obvious case of that. So we'll tackle these two problems during the rest of the time of my presentation here. And just the first one is the classical problem of the ball mill. The ball mill is very easy, straightforward, because we know who does transfer energy and we know who is there to accept the energy or absorb the energy. So DEM loves that because you just put the grinding media and then you calculate afterwards the outcome of breakage. So we use this approach of just using DEM to get the collision energy spectrum, and then we use our model that we just saw here to be able to calculate the outcome of each breakage event. Well, the tricky part is that in mills, particles are never alone. They're actually all in assemblies and in beds. So we had to understand a little bit what's going on here. But in the end of the day, we were able to use population balance models decoupled from DEM to predict results. So just this is the approach we have been working for a long time in a ball mill to be able to use DEM to do some fantastic things, which is what is the effect of mill diameter? What is the effect of mill length, liner profile, operating at different mill speeds, load, and size? DEM loves these variables. It can actually describe them quite accurately, their effect. And actually, we capture these as a function of distributions, different types of distributions, shear and normal, and so on. And of course, if you go just to illustrate here, very crazy profiles, but just to illustrate change in the line profile in a laboratory mill, you get obviously quite different distributions there. So this piece of the puzzle is well covered in ball mills. You can do that in very straightforward simulations. But now, how can we couple the two pieces of the puzzle together? As I mentioned, you have to describe what's going on in the bed level. So to be able to answer, which is how much material, Malcolm calls sub-DEM material, which is not in the DEM simulation, but it is, you have to account for that in breakage. How many particles or how much material is nipped in each stressing event? Our model actually was able to predict something like this, which is as you have coarser and coarser particles, less and less particles are nipped. As we have finer and finer material, bed is much more populated. Our models have been able to predict that, and doing some smart experiments, we have been able to validate in the lab. So we got this piece of the puzzle together. Great. Now we can go and solve the whole thing. Well, it's a little bit early in the morning to put some integral differential equations here, but the idea is just for you to understand, that's why I talked about population balance, because we wouldn't have been able to do this if we didn't learn about the traditional population, much simpler formulation. It is a population balance model here, which has this appearance and appearance terms, but of course these guys are quite nasty, highly convoluted expressions, but quite solvable, quite doable for a batch mill like that. And also, the nice thing is that it's quite explicit, the contributions of body breakage from surface breakage. These are individual components in the model, very nice and elegant. So, just to illustrate, we know for a long, long time from experiments and also from industry that if you put large balls in a mill, you're able to break at very high rates coarse particles, but to sacrifice breakage at fines. Whereas if you go to very fine sizes of balls, On the other hand, you do a very bad job breaking coarse particles, but you do a great job breaking the fines. Well, we know that. The thing is that this is all outcome of the simulations. We simulated this, didn't need to do experiments to show exactly what happens when you do batch grinding tests. So we are confident that the model makes sense. Of course, it's a very long story made short here, but of course quite a few students have been working on this. But we're happy that with some tweaks in the end, we were able to describe some extremely unusual experiments that nobody should do in practice, which is put very coarse particles with very small balls. But the nice thing is that if you want your model to be able to do fantastic things, you have to stress them to the limit. And when you get something like this, so that now I start to believe this guy, because traditional population balance model would be really doing a terrible job in this. So we got confident that it's doing a good job here. So we went to, of course, Vale, a good partner of ours, to predict very fine grinding here for pelletizing, did all the scanning, simulations, and then we could get some decent results out of this. These are all simulation results. There's just one point here for validated. But basically, we could understand the effect of mill filling on the proportion of fine material. So surprisingly, looking at lower fillings is beneficial. Mill speeds under the range was beneficial to increase the speed, whereas ball size, they already recognize that there's an optimal ball size, no benefit to going finer. So this is a model already applying to the continuous milling system, giving sensible results. So now, we thought that, well, let's try to use two different systems. I think another ball mill that we don't use in mineral processing is actually the Planetary ball mill used for sample preparation. Let's see, can we actually get this to be predicted using our model? We just went there for half a dozen different materials of very fine size and did testing on this just to see if the model can give anything reasonable, because we're going way out of our comfort zone here. And so, well, now the major question arises, how can you measure strengths of particles which are that fine? You cannot really even grab individual particles. Now, these days there are machines like this, which are basically indenters that have actually a blunt indenter to crush like a small compression testing. And so you can actually test particles one by one. And for instance, a small quartz particle, 40 micromole quartz particle, you can get exactly the force deformation profile and determine the amount of energy. It's a huge amount of work. Just as a proof of concept, we did this. So we convinced the student to do for half a dozen materials, and she was very keen on seeing that, can this stuff give anything meaningful? Yes, indeed. You see, rice husk ash here, we do have in Brazil, very, very easy to grind, very tough material here, which is the silicon carbide. It actually characterized all the range of the sizes and strengths, a lot of availability. But then when we simulated on DEM and put into the model, well, that's where things are not too straightforward. So of course, different things are going on there. The material capture in these mills is quite different, the slurry effect. But on the upside, when we look at the rates of breakage of those materials, they're definitely much higher than we actually predicted, but quite correlated. So it actually means that we're not too far. So the characterization, as far as it was in terms of material stressing conditions, squeezing very slowly a particle is quite different from actually hitting very hard. We recognize that, but still it's in the ballpark value here. It makes sense. And if we by any chance forget about those very difficult tests and just get the model that has 12 parameters, now just with 2 parameters for testing, just fitting 2 parameters for the test, you could actually calibrate for all different materials, size distributions. So population balance model, you need at least 7 or 8 parameters to do the same job. So it is quite promising even for this. Well, but of course we got even greedier to try to be able to tackle problems that in industry are much tougher, which is obviously the case of the SAG mill. SAG mill, traditional population balance model, has really a tough time to really deal with all the complexities of both the grinding media and the ore transferring energy. So a PhD, Rodrigo, actually did this work of coming up with a method of iteratively simulating DEM and then using the breakage model and then going back and doing another simulation just to get away from getting particles breaking inside the DEM. Why? Well, Malcolm and quite a few people know if you do a pilot test, if you put a particle there, definitely after 1 or 2 hours, you go there, back there, you may see that particle still alive. So it takes sometimes a long time for the charge to season. And DEM doesn't work with this 1 hour or 30-minute type of timelines. So we cannot really, at least it's not going to be my time, that we're going to be seeing millions of particles being simulated for hours in DEM. We have to be smarter than that and quicker. And this approach was an interesting one to be able to do that. So we did these different iterations, and we ended up actually being able to predict fairly well what actually the holdup inside that milk as a function of the feed. And of course the product just was assuming a given classification function. So it is still work in progress to be able to do this properly in an industrial environment, but the idea is already there. And so these, within the spirit of, we don't have to get the tools completely finished to be able to deliver value to industry, because sometimes people have to make decisions out of very little or no information. This company, Elecmetal, ordered us to actually get a post-processing tool for their DEM to be able to look at liner designs and have some guessing on how much energy is going to the different sizes. But at least from that, they can actually have an idea of the rates, expected rates of breakage for coarse, medium, and size material, and they're using their designs. But just the final part of my presentation is exactly the other part that I was missing, which is, what about those size reduction machines that you cannot decouple DEM from breakage? You have to put particles breaking inside DEM. A number of problems fall into that category, and those problems are the ones that we actually had to tackle. Well, the first thing we did is look at the softwares and realize that in no commercial software there was a proper particle replacement implemented. So we took advantage of our partnership with DEM, and actually with DEM Solutions, and actually got this implemented, as you see. And the other thing we did is, just as a naive comparison, can we already get something reasonable out of the softwares that are already commercially available? Because you see a lot of advertisement from them that they can do this, we can do that, but really we wanted to put another student, of course, to test this and see if they were already ready for that. And then in the end of the day, we ended up implementing a new software, a new model-based software. So the first thing is we contacted DEM Solutions that were interested in getting one particle replacement model implemented in their software, and we actually got a very simplified version of that, which is, in the end of the day, just having a particle. Every time it is stressed beyond a certain level, it creates a population of small progeny, and then keeps predicting what's happening in size reduction. How can we test that? The way we decided to test was to look for the simpler size reduction system, which is a piston and die. And here, even further, looking at iron ore pellets again. We don't crush iron ore pellets, but they're just nice and round, so we can even count them if they don't break. And so we did a lot of testing on this, and then simulated to be able to predict. You can see here, on the basis of testing single particles, when we simulated the bed, we got some quite reasonable predictions, which is, here the red line is the experiment, that is the force that you apply and the packing density, how much of the material is being squeezed, and actually pretty good predictions here with the simulation. And if you even further count the number of particles that broke as you increase the force, actually the fit was actually pretty good. So the model is giving a reasonable representation of something which is still a simple size reduction system. And this is all done in DEM. Well, so now we wanted to see how do these actually models already compare to each other. Are they ready to actually go for the next level to be able to predict really things in real life? So we compared these three different models. The bonded particle model, which is a model that has been used a number of times, very nice in detail, but very heavy computationally. This particle replacement that we've put together with DEM Solutions. And finally, this fast breakage model, which is actually the one that is available in Rocky, creates all those funny fragments. So we put this together, head-to-head comparison, and with the idea that, well, let's see how we fit the data to single impacts, so a single particle. So look there, just doing simulations like this. be able to predict, can the models actually be able to predict the particle size, the fracture energy distribution, as we mentioned, here the data, the symbols? Well, we could see that the models are still far from being able to do that, at least a couple of them. For instance, the particle replacement model that we implemented was way too simplistic, just a single value of energy broke on no breakage here. On the other hand, the triangles here, the fast breakage model in Rocky was actually quite reasonable, whereas the bonded particle model naturally doesn't have variability. You have to actually input that, but the complexity would be quite significant. So it's not too bad, but let's say that we got a fit here. But on the basis of doing this, we started doing some tests. And here you see bad breakage tests of real copper ore particles. And then looking at here, the same configuration as the computer. It was reasonable. We did a lot of measurement calculations there. But for instance, one measure that we did is how much the bed left an impression on carbon paper, for instance. It's a good idea of how much actually it squeezed the bed, how far it applied stresses. And here, this is the radius of capture. That is how the radius from the center. Experiments were done here, and then we got the simulations. Well, naturally, as you put more energy, you impact more materials, so you squeeze more particles. And actually, the models were kind of funny, not quite. But the bonded particle model was not bad at all. It was quite good, and the fast breakage model as well. So when we look at the size distribution coming from them, even with all the effort to try to reconcile, it became quite obvious here that the data are those triangles and circles, and the particle replacement was actually pretty good doing representing what came out of the tests for a given energy, but those two models were completely off in spite of a lot of effort that we put trying to calibrate them. So when we actually, and then we did a head-to-head comparison between the models. So it's quite obvious that there is no one yet that was ready to suit the needs for our simulations for comminution. So, but we got really fairly happy with the results from the fast breakage model in Rocky, but not completely happy with that. So when we contacted them, they said, well, if you have a complaint about our model, give us your model and we implement it. So, okay, they call this Tavares breakage model because it was done back in my day at PhD. So, and then they were kind enough to give us some money to test it if the model worked, because I was concerned about that. So now a student doesn't have to go breaking particles one by one. They just look at the particles being broken in the software and count them. And so we have to input the model parameters, but those are exactly the same model parameters that you've seen before. The same thing, we don't change this model for 10, 15 years now. And so what comes out of this is quite nice, because look at that energy applied and this amount of material broken for different materials. The model actually, the simulation does actually exactly what the model was meant to. And there's some work in progress here that the model is these lines and the simulation is doing something yet funny here. They're working on this. But this is quite enticing that it's actually being able to represent from a single particle breakage level what's going on there. So when you look at the size distribution, remember, DEM for size distribution is pretty tough because you cannot have the full spectrum of sizes, just truncate at a given size, for instance, 0.3 millimeters. But you see, it's not bad at all, actually. Look at very low energy impacting the particles. The points are the experimental data, the model, and here are the simulations. If you look at 0.05 kilowatt hour per ton all the way to 3.45, it's not bad. It's going to be doing a really good job looking in a crusher, as we are going to be doing in short time. Now looking at that weakening effect, because we know particles get weaker and we input our model there. Well, a student divided this virtual set experiment here, just dropping particles over and over again, and then looking at the number of impacts as a function of the amount of material broken, pretty good as well. So the model is already representing that with a single parameter, which we're very happy about. Well, what we're doing right now is, now sponsored by these guys, to look at different crushers. This is not yet breaking anything, but it's actually just the structure of the DSI and then the gyratory cone crushers that we're going to be simulating in the next several months. So this is how we're going to be applying this. Well, just a final part of my presentation on this mechanistic modeling is looking at the most challenging from the breakage side machine we could come across. Why? First, because in HPGR you have to really have particles breaking, quite obviously, because otherwise they won't go through the gap. So you have to have particles breaking there. But on top of that, we know that the movable row actually responds to the stresses. So you cannot just freeze those rows, you have to allow them to move. That seems like an obvious thing in simulation, but it's something that DEM doesn't do by default. You have to tell it how to move parts which are meant to be just hanging there. So we work with the DEM solutions and sponsored by Vale to be able to introduce this motion of the row. And that actually required to put an API and with this model, this custom equipment kinematics there to explain how the row moves. It's basically a pneumohydraulic system. And then using this API, using DEM, we could actually implement it exactly what you see there, the relationship what happens in a bed and what happens in the pneumohydraulic system. So this we did with them, and we applied that. Remember that this was done with the company, and now they have this for free. Anyone who actually has the software just downloads our solution. A couple of people already around the planet use that we developed with them, exactly this model. So for instance, if you have here in these simulations, you can get some nice things, which is the profile, force profile, which we know along the axial position, close to the edge, low pressures, close to the center, high pressures. But the most fun thing from this is exactly, since the model is responding to the material and it's dynamically responding, we can actually have something like that, which is, let's see, the grayish material here is actually softer, and the harder material is the darker one. As we actually move through the rows, you see here the percentage of dark particles or hard particles actually going through increases from 0 to 100. But then you look at how the gap responds. The gap changes the level because actually it's dealing with a much harder material or much stiffer material. And the forces, of course, it goes all over the place, but it's still exactly increasing the force because it's dealing with a stiffer material, and the power is like, no comment at all. But really there's a lot that can be gathered on this, and we're doing a lot of work in this area to be able exactly to harness as much information from a simulation as realistic as we can to be able to apply it to solve real problems. Well, so just coming to my conclusion is that I think, looking at the title and Professor King's review back 25 years ago, I think there's definitely been a lot of advances from our group, but of course from a lot of people who have been working in this approach in the mechanistic model comminution. I think there's obviously a lot still to be done, and a number of areas in this. In particular, I'd say definitely liberation is not yet been implemented at all into this model, is a key thing. And of course, the whole business of describing how the air and the slurry flow, so SPH and other techniques have been used, but not yet fully implemented to the level of predicting breakage. So this is an area that I think is really a good area to invest. I'd say there's definitely no shortage of opportunities for development. A number of size reduction machines we have, and even those that we have been tackling, there's still aspects which are not yet satisfactory. And our approach at UFRJ is to be able to, as soon as we have something usable, give it out to the world to be able to test this, because I think a lot of people are keen in trying to solve actual problems, and these tools, for instance, the multi-body dynamics coupling is already very accessible in DEM. The breakage models we developed, you can find them in DEM, but certainly not in Rocky, in the latest version. And we're happy here that through P9, in the next several months, we'll put the first version of our model in IS. So I think after 25 years, we might be in a moment that we finally are able to get the first mechanistic model of a mill available for circuit simulation. Because I think Malcolm is quite right when he says that a model is quite fine, but unless you put them talking to the rest of the circuit, you don't harness as much value from it. So that's what we expect. It's not a small task, but I think it's a great challenge that we are looking forward to meet. So just acknowledging all the sponsoring companies. P9, of course, with all the sponsors, and Vale, the Information Atomic Rocky, ESSS. But of course, this is not the work of myself. There's been quite a few people in the lab. This is the latest team, and we're very happy to be commemorating 10 years of LTM. We started exactly 10 years ago, and a lot of work has been done there, a lot of bright people. We are very happy that a lot of these bright people are already in different parts of the planet, cross-pollinating, and we're more than happy also to have new bright people joining our group. So, thank you.